my name is Nicholas Droppelman, and today we're going to be going over density and pressure altitude. Our sources for today are going to be the PHAK, or the Pilot's Handbook of Aeronautical Knowledge, chapters 4 and chapters 12. So the first thing that we want to talk about is kind of why we care about density and pressure altitude. These are going to be two atmospheric conditions that directly affect our aircraft's performance, so our ability to take off, our ability to land, and our ability to climb after takeoff. So the first thing that we want to talk about before we get into specifically the altitude aspect of it is what is density. So density is going to be kind of defined as how tightly the molecules of air are packed in a given area. So if we draw like a little square up here, draw two, kind of have two different scenarios. We can have a scenario where there's very few molecules in an area, so maybe like 4, kind of something like that. We're going to have a lot of molecules kind of distributed in that same area. And so that's going to, in the case where there are very few molecules, that's going to be a low density. In the case where there's a lot of molecules, that's going to be high density. So now, why do we care about whether it's low density or high density? Well, our aircraft directly relies on the air around us to create performance, right? That's why it's an airplane. So we need it for lift, we need it for thrust, and we need it for engine power. So kind of how these affect those are, with lift, our wing relies on the air going underneath it to exert a force upwards and push us upwards, which is what lift is. And so if we want to create the most amount of lift, then we want more air molecules to be able to exert more force on the bottom of our wing, lifting us up. So that means that in a high density environment, we will be generating more lift. In a low density environment, we won't be generating quite as much lift. We'll still be able to generate some, but especially depending on the difference, will not be generating nearly as much. Next, we want to talk about thrust. So the propeller on an aircraft is essentially just a small wing that we attach to the engine and take it from vertical to horizontal. So that means that it's going to be affected in kind of the exact same way as the wing would be, with a lot more air molecules packed together and more density, more dense air. That propeller is able to have more air molecules exert a force on it, creating more thrust, allowing us to take off sooner and climb faster. And then lastly, we want to talk about our engine. So our engine relies on air and fuel to mix together, and then we combust that. And so if we want to burn more fuel, which is what's going to give us more power, then we need to have more air present because we need to keep a consistent ratio. And so in that case, if we need more fuel, then we're also going to need more air. So high density is able to pack more air molecules into the engine, allowing us to burn more fuel, creating more power, again letting us take off sooner and climb a lot faster. Alrighty, so the next thing that we're going to want to talk about is how we change from low density to high density, because it doesn't just happen by magic, right? There are kind of 3 main things that are going to affect the air density. Those are going to be the pressure, the humidity, and the outside temperature. So the pressure affects the density because if we have a higher pressure, which means just more kind of force, then it forces the molecules to pack tighter into that area. Whereas if we have less pressure, then those molecules are allowed to expand more, meaning that we're going to have a lower density. Next thing that we want to talk about is humidity. So humidity does affect density. It's not a massive effect on it, but it does have an effect on it. As we get more humid air, that density is going to decrease, and that's just because the water molecule actually weighs less than the oxygen and nitrogen molecules present in the atmosphere, which oxygen and nitrogen make up most of the air that is in the atmosphere. And lastly, temperature. So temperature is going to affect the density because as molecules heat up, they move faster. And as they move faster, they begin to kind of pull apart. So that would lead to a lower density. So as the temperature increases, they move faster, the air molecules spread out, and we get a lower density. As the air begins to cool back down, they will slow down, compact a little bit tighter, and we get a high density. So now that we understand a little bit about density and how that affects our aircraft, next thing that we're going to want to talk about is pressure altitude. So pressure altitude is defined, pressure altitude is defined as the height above the standard datum. So what that means is that we have what's called the International Standard Atmosphere, or the ISA. And so that's just kind of a very generalized representation of what the atmosphere looks like in perfect conditions. And so the standard datum is going to be what 0 feet of altitude is in those perfect conditions. So that'd be something like right here. That'd be our standard datum, or 29.92 inches of mercury. Now, one thing about the pressure in the atmosphere is that it decreases as we climb in altitude. So if this is 29.92 down here, as we get up here, it'll be a lot less. And it actually decreases at a fairly standard rate of about 1 inch of mercury per 1,000 feet. So say that this is 0 feet and this is 5,000 feet, well then we can take off 5 inches of mercury, giving us 24.92 inches of mercury at 5,000 feet. This would be 0. And so kind of knowing that, we can use it to kind of start to develop a understanding of how our aircrafts can begin to perform as we climb in altitude. Because as we talked about with density, one thing that affects the density is the pressure in the atmosphere. So if we're flying at 5,000 feet, where the pressure, is a lot less, then the density is also going to begin to decrease. So we're going to have lower climb rates. If we're taking off from an airport that's at 5,000 feet, somewhere maybe out in like Colorado or out in the mountains, then we're already kind of starting off from a point of degraded performance, versus if we were taking off somewhere like down here in Florida, where most of our airports are roughly at 0 feet of elevation. So we've got that kind of change in performance between those two. Alrighty, now that we understand a little bit about pressure altitude, we can start to talk about density altitude. So density altitude is going to be defined as pressure altitude adjusted for non-standard temperature. So, as before, when we talked about the International Standard Atmosphere, we talked about that 29.92 inches of mercury being the 0 point. Well, another part of the International Standard Atmosphere is the temperature. So that's defined as 15 degrees Celsius. So that's what truly gets it to 0. So now that if we start changing the temperature, because obviously every day is not going to be the exact same temperature and be that same standard temperature, now, like we talked about before, it'll start to affect that density of the air along with the pressure. So that's where we find out what our pressure altitude is, which I'll get into in a minute, and then to get our density altitude, we adjust it for that temperature, which gets us kind of the full picture of how the density of the air around us is going to be affecting our aircraft performance. And kind of another good way to look at density altitude is the altitude that the aircraft feels like it's flying at. So, as we talked about before, we've got those two boxes, we'll put some air molecules in them. We've got low density and high density. And low density is going to be from those hotter temperatures. High density is going to be from the lower temperatures. And so, as we talked about, we want that kind of very high dense air or high density air for our better aircraft performance. So, as our temperature begins to go up and our density decreases, that's also going to increase our pressure or density altitude, because that begins to thin out the air and begins to make the air kind of the same density as what it would be at, say, 5,000 feet, even if we're standing at 0 feet, right? So that's why we really start to care about density altitude, is it's going to be, as we get hotter and that density gets lower, our density altitude gets higher. It can be a little bit confusing at first, but just remember low density, high density altitude, thin air, high altitude, kind of a good way to think about it. And so that begins to, again, lengthen that takeoff roll, begins to lengthen that landing roll, worsens the climb performance. So if we've got obstacles around us, then we really, we want to start figuring out what that all is so we can make sure we can clear those obstacles. If we're on a short runway, we need to know that we can stop in time, that we can get off the ground in time. Just kind of stuff like that, right? And so where this really starts to affect us, kind of the worst case scenario, is starting off from a high altitude airport with being very heavy, because as we're heavy, we can't accelerate as fast, we can't climb as fast, and then being in a high density altitude situation or low density. Now, whether that's because there's low pressure, because there's high temperature, a combination of the both, that's something where we really want to start digging into the books and making sure that our calculations are correct. Alright, now that we understand a little bit about density and pressure altitude, we can get into actually how to calculate them, so that way we can know our performance for the day and whether or not it would be safe to fly. So the first thing that we're going to calculate is going to be our pressure altitude. And we can calculate that kind of two different ways. So the first and easiest way is going to be to set our altimeter to 29.92. Whatever altitude it reads is going to be our pressure altitude for the day. Or if we want to calculate it by hand, we can use this equation here, where we take our standard pressure of 29.92, we subtract our current altimeter setting, which we can get from the METAR or the ANIS, or kind of the local weather. We'll multiply that by 1,000, which gets us into feet, and then we'll add the field elevation to it, giving us our final pressure altitude. An example of this would be if we're here in Daytona, the field elevation is going to be 32 feet, and we'll say that we have a current altimeter setting of 28.92, so a little bit of a low pressure day, which means that our pressure altitude is going to be a little bit higher. So we'll take 2992, subtract 2892, which gives us 1. Just kind of try to keep the math a little bit simple. Multiply that by 1,000, keeps us at 1,000, and then we add our field elevation to it, which brings us up to 1,032 feet. So we have a little bit higher pressure altitude for the day, which means that we can kind of already start to get the picture that our plane's going to have a little bit degraded performance for the day. Next, after we've found our pressure altitude, now we can move on to finding our density altitude. So this can be found through a number of ways. Kind of the easiest is going to be through the electronic flight bag, or such as like ForeFlight, where it can read it to you on there on the weather information section, or through like the METAR. The next, we can calculate it through the E6B, either manually or digitally, or we can use a density altitude chart. Those are going to kind of all be the easiest ways, but if we want to do the math and calculate it out for ourselves, we can totally do that as well using this equation here, where we take our current pressure altitude. So if we kind of use this same example, so we'll take 1,032, you add 120 times whatever the outside air temperature is, minus the standard temperature. So we'll say it's about 20 degrees out, so it's a little bit of a hotter day. Then we'll subtract out the standard temperature, which we're at 0 feet of elevation, so it should be 15 degrees Celsius. And one thing that I forgot to mention when we were talking about density altitude and kind of density is just like how the pressure is going to decrease as we climb in altitude, so will our temperature, at a rate of roughly 2 degrees Celsius per 1,000 feet. So if we were taking off from a runway that was, say, 2,000 feet in the air, instead of it being 15 degrees, it would be 11 degrees, because 2,000 feet plus 2 degree difference per 1,000 feet, so that'd be 4 degrees difference. 15 minus 4 is going to be 11. But bringing it back into our example here, where we're kind of at that standard, or at 0 altitude, at sea level, now we can kind of do the math. So we're going to get 120 times 5 plus 1032. Excuse the little bit of crookedness right there, which gets us 600 plus 1032, which gives us a final density altitude 1632. So 1,632. So if we were going to fly on this particular day, when we go to take off, our aircraft would feel as though it's taking off at 1,632, even though our airport elevation is only 32 feet. So that concludes our lesson, and I hope it was useful. And with that, yeah, have a wonderful rest of your guys' day.